Sorry for the inconvenience. Actually, I lost my internet connection. So yeah. So I was explaining that optical rotation arise because of the difference in the refractive index. Refractive index is nothing but the difference in the speed of light in that medium. So we saw that it continues to be in a circular motion, but one part is moving faster compared to the, say for example, LCP moves faster compared to the RCP. So only it would be having this kind of thing. So we were expecting like this way, circular motion and a plane polarized light, but actually it rotates to either right by a phi angle or it rotates to left angle, which is phi. So this happens because of the change in refractive index. So option is B. Is that clear? Absorbance is related to ellipticity. This refractive index is related to your optical rotation. So these two phenomena you need to remember that phi, which is optical rotation, is dependent on refractive index difference, and psi, which is ellipticity, it is dependent on absorbance. So is that clear?
Clear, ma'am.
Okay. So the next question is, the helical motion of a molecule is possible only when. So we understood that a plane polarized light helical motion, we saw that it is a part of RCP and LCP. Now in the molecule, when we were talking about whether it is having a helical motion like this way, why it is having. So we talked about two vector moments, mu E and mu M. So the first option is both the vectors should be absent. Second option is both the vectors mu E and mu M, which is the electric and magnetic dipole moment, they should be present. Only mu E should be present or only mu M should be present. So what do you think that this helical motion is because of what? Only this, both of them, or none of them?
Only mu E, ma'am. The electrical dipole moment only percent.
Okay, but just see the helical motion. We are not just talking about the transition angle, transition moment. So helical motion could only be possible that mu E will give you a linear transformation. Okay, you have to move linearly. But what about the circle thing? It will come from where?
Magnetic dipole moment.
Yeah. So for the magnetic dipole moment, it will give you that circular motion, and moving towards the straight line, it is giving you it is coming for the mu E. So now what should be the answer? Like only one should be active or both of them should be active?
Both of them.
Yeah. So both of them should be present. That's why in case of the chiral molecule also, when we were looking at the point groups, there we saw that both mu E and mu M vectors should be present. Now the next question is the ellipticity factor that we saw, that we understood that psi is related to the absorbance change. So its formula and this factor actually depends upon which of these equations, whether it is a division AL by AR, whether it's like this one, AL minus AR divided by AL plus AR, or it is AL minus AR or AL plus AR. Which option is right? So this, I think you can go back and read also. This is actually dependent upon AL minus AR, where if you remove this proportional sign, it will be 180 degrees into 2.303 into this AL upon AR divided by lambda. So this is actually dependent upon this difference of AL minus AR. So that is ellipticity. It is not the division. It is not the division of AL minus AR. This is the tan phi, which we saw that perpendicular divided by the base. And this value is actually your phi value. Is that clear?
Clear, ma'am.
Okay. So the sixth question says, now again we are coming to the, okay, we actually have not discussed this point. These questions I will take up in the next lecture because I had to complete that points first. So this psi, phi and lambda, that wavelength relation comes when we will talk about the circular dichroism and how the graphs look like. So actually when I'm talking about the absorbance, it is like this way. So this would be your absorbance. This is intensity and this is your lambda. And when I'm taking a optical rotation, there would be two enantiomers. First will go like this way. Another will go like this way, the opposite direction. Okay. So this is one enantiomer which is going like this way. And the other one is, this pink one is enantiomer 1. And this is enantiomer 2. and this is your phi, which is positive and negative. So if you will see at this particular point, if I would have drawn at the particular superposition to each other, so this is your lambda max, and lambda max, you are getting the phi value as 0. This is your axis where phi is your 0. So the question is, choose the correct match. Phi is 0 when delta is 0, lambda is 0, no. Phi is 0 when lambda is maximum, which is right. Here at the maximum absorbance, your phi optical rotation becomes 0. This is true, the option B is correct. Whereas phi is negative when lambda is max, only one answer could be possible. At lambda, when absorbance value is maximum, your optical rotation becomes 0 because you have two enantiomers and both are moving opposite to each other. If one is giving you positive side, other rotation would be negative. Both will cancel out each other. So the phi becomes 0 at this particular point. But if you will go at this sign where lambda is 0, this is still having some curve which is going parallel to each other. So that is called as a plane curve. This I will take again in the next live session where we will talk about. This is the kind of example of sucrose. As I was saying, no, when we are having a sucrose solution and we are passing the light and we saw that lambda, even if there is no absorbance, that means absorbance is 0 at these points. And at these points, still we have some kind of rotation, either towards positive or towards negative. That is because it is a chiral molecule. But when we have a lambda maximum, wavelength as a maximum, the absorbance is maximum, at that point, both the enantiomers of it will cancel out each other's rotation. For right side and left side cancels out, and therefore we get a phi value as 0. Is that clear?
Clear, ma'am.
Okay. In the same graph, if you will see, I have jotted down as a positive and negative sign. This is dependent on the right side rotation or the left side rotation. So when this pink one, if you will see that enantiomer 1, it is going from this value positive, it is crossing the 0, it is coming to the negative region. So whenever the graph goes from positive to negative, this is called as negative Cotton effect, which is being given by the scientist Cotton, who defies this thing. Like going from change of the phi value from positive to negative, that is called as negative. And if it is the reverse, if I'll talk about the enantiomer 2, it is coming from the negative, passing through the 0 and going into the positive, that is positive to negative to positive, that is called as a positive Cotton effect. So wherever if it ends, from there you need to remember which kind of effect is this. So that is a question. You need to match, you need to have a correct match. Positive Cotton effect is from phi goes from positive to negative. Is that correct?
Correct, ma'am.
No, read it carefully. I'm talking about positive Cotton effect, and the phi has to go from positive to negative. That means if I'll start with a positive and I'm going to negative, now the final destination is negative. So the negative, when I'm reaching the negative, it can't be called as a positive Cotton effect. It is going from positive to negative. So wherever the final destination is there, that is your name. If it goes from positive to negative, it is the final one, that is called as negative Cotton effect. If it is coming from negative to positive, final destination is positive, then it is called as positive Cotton effect. Now see the first option. It says positive Cotton effect when phi goes from positive to negative. That is wrong. The second option says negative Cotton effect when phi goes from positive to negative. Is that right or no?
Ma'am, here positive means what, ma'am? Negative means what, ma'am?
Positive is your phi value. Your optical rotation is either in right direction or it is in the left direction, right? So these signs are just the right and left one. So if one enantiomer is going from this positive side to the negative side, it's rotating like this way, say for example, and the other one is going from this way. So these are just the directions. So the question is Cotton effect, and the terminology, if it is negative Cotton effect, the final destination of that rotation has to be negative. So the B option, if you will see, it is from positive to negative. That means that is your this option is right. Is that correct?
Yes, ma'am. Correct, ma'am.
The C option, if you will see, the positive Cotton effect is when phi is going from negative to positive. Is this correct? The final destination is positive and the name is also positive. Is it correct?
No, ma'am.
No, it is also correct. No, see, when I'm talking about, you just need to define positive Cotton effect. That means the phi has to come to last in final stage has to be positive. When I'm talking about negative Cotton effect, it has to come to negative as a final stage. So if you said yes for the B option because negative Cotton effect is from positive to negative. Negative becomes your final. That is right. Similarly, if I'm talking with the positive Cotton effect, it is going from negative to positive. Now, positive is your final destination, and we are talking about positive Cotton effect only. So this option is also right.
Okay, ma'am. Both B and C correct, ma'am.
Yeah, both B and C correct. So that means option D is the right option. Is it understandable now? Any confusion?
Understand, ma'am.
Okay.
No confusion.
Now, the two questions, these are kind of easy because we just discussed that from the concept of the character table, for a molecule to be CD active is nothing but your circular dichroism. And we know that circular dichroism is an effect from the ellipticity. Right? And for that matter, we said that mu E and mu M both should be active. And in that particular case, we saw that X Rx, Y Ry, and Z Rz should be having similar kind of irreducible representation. They should be having same symmetry, irreducible representations, right? So now the option says all the three pairs. Now, firstly, see the three. What are the three pairs? X and Ry, Y and Rz, Z and Rx. They should have same symmetry, irreducible representation. Are these pairs correct?
Yes, ma'am.
See them carefully. What are the pairs I'm taking? X and Ry. What are the pairs that we actually look into? They should be having same axis. X and Rx, Y and Ry, Z and Rz. But the first option says it is X and Ry pair. So are they correct?
X R Y R Z Z R X.
See, the pairs have to be having the same axis. X and Rx should be having same symmetry, not X and Ry. If X and Ry are having the same thing, then this C2V should have been chiral. See in this one, X and Ry, this one, it is having B1. But we said C2V is not chiral. Why? Because X and Rx should be in one group, Y and Ry should be in one group, and Z and Rz should be one group, which is in this case. Z and Rz is having A2, X and Rx both are in E, Y and Ry also are in E. That's why this is chiral and this is not chiral. So when these kind of questions are coming, there also you have to be very careful. Read this. The pairs that have been given. It is written that all three pairs should have same symmetry, irreducible representation, but the pairs they have taken, that is wrong. They have taken X and Ry. We need X and Rx. So just find out whether X and this one, option C, X and Rx, Y and Ry, Z and Rz, they should have same symmetry, irreducible representation. So option C is correct.
Yes, ma'am.
Also consider the option B. It is saying any of the two pairs, X, Ry, Y, Rz, Z, Rx, firstly, the pairs is wrong. Secondly, all three of them should be having like X and Rx should be in one group. R, Y and Ry should be one group. It is not, it can't be like this way, like X and Rx are having same symmetry, Y and Ry are having same symmetry, but Z and Rz are in different group. So that way also, it can't be a CD active. So all three of them should be having similar kind of symmetry. They could be different among themselves, but the pairs should be having similar kind of symmetry transformation. Is that clear?
Clear, ma'am.
Okay. So the last question, out of the following, which molecules can be CD active? The circular dichroism, for that activity, we need to have mu E and mu M active. And for that, X and Rx, those pairs that whatever we saw in the question 8, that should happen. Now, instead of the point groups, they have given the molecules. So you need to first define the point group of this molecule, and then you need to define whether it comes under CN category or DN category or not. So water comes into what category? It is a which point group?
C2B, ma'am.
Huh. So C2V is CD active.
What, ma'am?
Is C2V point group circular dichroism active? Is this chiral?
It is achiral, ma'am.
Chiral only CN and DN. Now this chromium ethylene diamine complex. What is the point group of this? We have discussed this in I think second week or third week. So this is a kind of this molecule. There would be ethylene diamine and just bidentate ligand. So chromium, nitrogen, other pair, and other pair. So it is having D3. You can go back and find it out by yourself. So this one is having D3 point group. So will that be CD active? Circular dichroism active means it has to be chiral. So whether when it has been asked whether it is CD active or not, that means whether it is chiral or not. So whether this molecule having D3 point group, it is CD active or not.
CD active, ma'am.
Yes. The other one, this is chromium and ligand. This is an octahedral symmetry. Whether this is CD active or not.
Inactive.
Sorry. What is your answer? I didn't hear that.
Ma'am, the octahedral complex of chromium NH36 is superimposable mirror images. So it is achiral.
Anyway, it is
So-
not belonging to the CN or DN point group, so it is not a CD active thing. And the last one is CH4. CH4 will be having tetrahedral. Sorry, CH4 is having tetrahedral point group. So tetrahedral point group is chiral or achiral?
That is achiral, ma'am.
So it would be also CD inactive. So only option is
CD
B.
inactive one. B is correct.
So only the B option is correct. So I would suggest you go back and do practice of many examples, which are the chiral point groups, which can be called as CD active. See their character tables, and next lecture we will be taking up the one first half. We will talk about the character tables to make you guys more understandable. So other than that, is there any confusion regarding what we understood? Because today we covered a lot of concepts regarding the optical rotation, ellipticity, light matter interaction. Then we saw whether how to consider the mu dipole moments, electric dipole moment, magnetic dipole moment vectors, and how to quantify them, how to see the character table, how to give the representations, and which molecules are CD active or not. So all these concepts we have covered so far. I hope you guys have understood. Is there any question that you want me to explain again?
Okay, ma'am. All the things I understood, ma'am.
Okay, great. So in 5 minutes, the live session would be finished. So if you want to continue be here, you can stay. Otherwise, you can leave the meeting. I will be uploading up this in the YouTube channel. So you can again go back and rewatch these videos and also the professor's video so that you will be in touch with all the concepts. And I would suggest revise again and again and come up with more questions in the next live session so that I can help you guys in understanding better. Okay.
Okay, ma'am.
Okay. Thank you for joining.
Thank you, ma'am.
So with that, I am ending the session. I hope you guys have learned something. And if you have any other doubt, you can come back again in the next live session, which is next Saturday from 7 to 9 p.m. I would be happy to answer your questions. Thank you for joining me.